In this project, I used the trajectory optimization technique, direct collocation, to generate a trajectory for a planar ballbot. Then, I stabilized this trajectory using a time-varying linear quadratic regulator. I modeled the planar ballbot using the standard manipulator equations, along with the term to represent velocity-dependent friction on the ball and the head. The state of my robot includes theta as the angle the ball has rolled, phi as the angle of the head off of the vertical, and both of their corresponding velocities. This system has a single input, the torque applied from the head onto the ball. To create the trajectory, I used a technique called direct collocation. This converts the robot's dynamics into a nonlinear optimization problem. In this case, I wanted to find the trajectory that minimized the square of the input torque while obeying a few constraints. The first set of constraints are the start and the end points of the robot. The initial state constraint says that the robot must be near the zero position, allowing for a bit of wiggle room. The final state constraint says that the robot must end up rolling between 2 and 3 radians, with the head nearly vertical. The final constraint is that throughout the entire trajectory, the robot's head must not go farther than 0.5 radians off of vertical. This is to make sure the robot does not fall over. Solving this optimization problem resulted in the following trajectory. Many other ball balancing robots lean the head in the direction of motion when they drive around. You may have noticed that my simulated robot does the opposite. I think that this is because of the fact that I set all of the masses, lengths, and inertias to 1 in this project for simplicity. This is good so far, but models do not perfectly reflect reality. The next part of my project is to apply this trajectory to a slightly different 2D ballbot to show what happens if the model is incorrect or there are disturbances. In this model, gravity and the drag between the ground and the ball are both 50% larger. Also, the ballbot's initial state is exactly 0, instead of the first step of the trajectory. These changes mean that the robot only travels around 1.5 meters and falls down at the end. To make the modified ballbot follow the trajectory better, I added a time-varying linear quadratic regulator. This creates a controller at every time step to push the robot back towards the trajectory if it begins to drift away. This drastically improved the ability of the robot to follow the trajectory, and the robot does not quite fall down at the end. However, there is definitely still room for improvement in creating good trajectories and improving the time-varying linear quadratic regulator.